A daring mission to reveal secrets of our solar system's distant past
Asteroids are actually tracers of our history.
and help safeguard our future.
Asteroids might strike the planet. The damage created by that would be absolutely enormous.
Can this spacecraft unlock this asteroid's secrets by grabbing a piece and bringing it back to Earth?
This has really proven to be difficult.
We literally expected this asteroid to look like a beach. That is not what it looked like at all. It's just rocks everywhere.
Oh my gosh, those big boulders were just not what we were expecting to find.
When we go to see an asteroid, all our assumptions are usually totally messed up.
There's a million things that could go wrong, and the show could be over at that point.
Touching the asteroid, right now on Nova.
We spent years preparing for this, analyzing every scenario. It's very nerve-wracking.
This is an object we've never been to, something that's never been done before.
We're really pushing the envelope of what the spacecraft and the team can do.
I'm very excited and also very nervous.
You've got to persist at it, you got to know what you're doing, and sometimes you just have to be lucky.
More than 200 million miles from Earth, a spacecraft named OSIRIS-REx approaches an asteroid. In Littleton, Colorado, a team of space explorers nervously waits, hoping their spacecraft can do something extraordinary. Grab a piece of an asteroid named Bennu.
OSIRIS-REx is going to be the largest sample collection robotically in the history of solar system exploration.
If all is working as planned, the robotic explorer is reaching for the surface, grabbing as much rock, dirt, and dust as it possibly can. Just 5 seconds later, it will retreat. OSIRIS-REx must complete this critical task totally on its own, with no human at the controls.
We won't know what has happened until we get away from the asteroid surface. This is a really nail-biting moment.
Once the spacecraft safely leaves the surface, it will store its precious cargo and bring it back to Earth. Even a small handful of asteroid dust could answer big questions.
It's really amazing that these tiny specks of dust grains can tell you so much about how our universe formed, how our solar system formed, how asteroids like Bennu formed, and how Earth formed.
They could even provide clues to how life emerged on our planet.
There's truth out there. There's an objective reality, and all you need to do is go out and find it.
Other missions have gone in search of that truth before, attempting to grab bits and pieces of distant space rocks. Back in 2004, the Stardust spacecraft flew through the tail of a comet.
It had a tennis racket type of a collector, is the best way to describe it. It was a grid, and it was able to put that grid out as it flew through the comet tail and collect those particles, stow it into its sample return capsule, and return it to Earth.
While it was an arduous task to find the microscopic particles trapped inside the grid, researchers made profound discoveries that have revolutionized our understanding of solar system formation, with about 1 milligram of space dust. In 2005, the Japanese Space Exploration Agency's Hayabusa mission attempted to grab a piece of an asteroid named Itokawa. The mission was filled with mishaps.
there were a lot of troubles. We had a lot of discouragement or disappointment.
Hayabusa was like Apollo 13. It was a successful failure. I mean, they had so many things go wrong, yet they still managed to get the spacecraft back to Earth.
It was a first. Bits and pieces of asteroid dust and dirt were brought back to Earth. But their take was small. Only about 1,500 tiny grains of Itokawa.
The Hayabusa samples were specifically grains that are between 20 and 100 microns in size. So just to give you an estimate of how small that is, diameter of human hair is between 100 to 200 microns in size. And so we're looking at particles that are half the diameter or smaller.
The amount of asteroid dust OSIRIS-REx could scoop up is enough to fill a few grande-sized coffee cups.
If we were able to collect that much material, it would be orders of magnitude larger than any other sampling ever done at any asteroid anywhere ever.
In fact, it would be thousands of times more and could reveal mountains of solar system secrets.
10 seconds. 9, 8,
September 8th, 2016.
4, 3, 2, 1. And liftoff of OSIRIS-REx, its 7-year mission to boldly go to the asteroid Bennu and back.
There is nothing quite like launch. The power of a rocket is immense, and even if you're several miles away from it, you really feel that, in your body.
The only way I can describe the experience is transcendental, because your whole career has led up to that moment, and there's a million things that go through your mind that could go wrong, and the show could be over at that point. So you kind of just have to reach that peaceful moment inside yourself and enjoy it, experience it, and whatever's going to happen is going to happen.
OSIRIS-REx has gone supersonic.
As an Atlas V rocket hurls the spacecraft out of Earth's orbit, the people behind the mission trust that math and gravity will guide it across millions of miles to its tiny target.
The first several months of the mission went very smoothly. The spacecraft was slowly approaching Bennu.
The next step now is all eyes on the prize, focused on collecting the sample and bringing it back to Earth.
Why are we going to Bennu? What makes this asteroid so intriguing?
One of the first jobs I had on this mission was actually to find an asteroid that we can go to. And you would think that would be easy. I mean, like nowadays, there's almost 1 million asteroids that we know about.
Like Vesta, pockmarked with craters. Potato-shaped Ida has its own moon. Chariklo is the smallest known celestial object with rings. But scientists have had their eye on Bennu for over 20 years.
From Earth, Bennu is a barely discernible dot of light. Even from Earth telescopes on mountaintops, you really can't get a good picture of Bennu.
Why then is this mysterious dot in the night sky 1 in a million? 1999, the Arecibo Radio Telescope and the Goldstone Deep Space Network took this series of radar images of Bennu. Although grainy and pixelated, they start to paint a picture of this tiny asteroid.
We were able to map its shape and its rotation and really get a pretty good idea what size it was going to be and what the overall structure of the asteroid was going to look like.
Bennu is shaped like a spinning top. It completes a full rotation about every 4.5 hours. When it comes to its size, this space rock isn't much taller than the Empire State Building. But it's Bennu's location that really piques the team's interest.
Typically, when we think about where asteroids exist in our solar system, we think about the asteroid belt, which is a region in space between the orbits of Mars and Jupiter. But there are a whole class of asteroids like Bennu that we identify as near-Earth asteroids because their trajectory brings them close to Earth at some point.
There are more than 20,000 near-Earth asteroids. The closer an asteroid is to Earth, the easier it is to reach with a spacecraft.
You're limited by the rocket you can use. You're limited by how long the mission can be, because, you know, time is money. So if you want to go to easy to get to accessible objects, they have to be really close to the Earth.
Of course, if an asteroid is in our neighborhood and easy to get to, that can also mean it's easy for the asteroid to get to us.
65 million years ago, an enormous asteroid crashed into the Earth, creating an enormous cloud of dust and dirt that blocked out sunlight all across the planet. Vegetation could no longer grow in adequate quantities to keep the herbivores of the planet alive. So there was an enormous extinction event that took place. We mark that period of time as the end of the era of dinosaurs.
This asteroid did a lot of damage from which, modern-day society would not survive.
There is a real threat. We know that. I mean, we can see the scars on the planet. The planet has been hit before. It will be hit again.
Researchers predict that as early as 2175, Bennu's orbit could be on a collision course with Earth.
Should that happen, the damage created by that would be absolutely enormous. The energy that it would release would be equal to 1,200 megatons of force. That's larger than all of the nuclear explosions since World War II.
It's not going to end life on the planet. That is not going to happen. But it does have enough energy to wipe out a city. If it hits on a populated area, that city will be gone.
We need to take this seriously. The chance of an impact is low, but the consequences are very high.
A deeper understanding of near-Earth asteroids could help future scientists design a mission to deflect or disrupt these potential killers. But they can also help reveal secrets of the Earth's distant past.
Asteroids actually are remnants left over from the earliest periods in the history of our solar system. They essentially have locked up inside them many of the secrets of what the solar system was like when it first began.
4.5 billion years ago, as the planets in our solar system formed, gas and dust stuck together, forming pebbles.
These are like the earliest formed solids that you can find.
Pebbles grew into boulders.
Of course, in all this mess, there's lots of collisions going on.
Boulders into mountain-sized asteroids.
You have all these asteroids hitting each other. You have protoplanets that are being hit by these asteroids. It's chaotic.
When the dust settled, the planets had taken shape. But there was plenty of material left over. Millions of small chunks of rock, metal, and ice.
These asteroids are actually tracers of our history. So if you take a planet is like an omelette.
A complex mix of ingredients, assembled bit by bit.
You start with 2 yellow eggs.
Perhaps a pepper, an onion,
salt, and possibly cheese.
You put them in a pan, it warms up, and then it's transformed into an omelette. So if I show you an omelette and you never saw eggs before, you will never be able to deduce that you started with eggs.
Just like an omelet, planet Earth's ingredients have been scrambled and cooked over time.
Earth has been changing. You have volcanoes, you have earthquakes, and it's difficult to know exactly what Earth was like at the very beginning of the formation.
Asteroids like Bennu, on the other hand, are remnants of that very, very earliest part of solar system history. So they're little time capsules that record what kinds of chemistry was present.
And they may contain some of the same key ingredients in Earth's original recipe, including one very special ingredient that none of us could live without.
We knew Bennu was very dark, and that was one of the prime reasons that we picked it. We think that means that it has a lot of carbon on its surface, particularly in organic molecules.
Carbon forms the backbone of all life on Earth. It's in land, air, and the ocean, and in every plant and animal. But how did it all get here?
It would be much easier if we could just say that carbon was right here to begin with. But if we actually look at the very earliest history of the development of Earth, the first 600 million years, this planet is entirely molten. It's a cauldron of lava and magma.
With surface temperatures estimated at least 3,600 degrees Fahrenheit, any carbon near Earth's molten surface would have evaporated into space.
So we still have this mystery on our hands. How did carbon get to this planet?
Did this key ingredient for life actually hitch a ride to Earth on comets and asteroids?
One of the ideas is that this impact brought all the elements that favored the emergence of life on Earth.
In 2014, one extraordinary mission of the European Space Agency named Rosetta found some important clues.
The intention of Rosetta was to land onto the surface of Comet 67P so that we could better study what the surface composition was like.
The mission made history when it dispatched a lander named Philae onto the surface of Comet 67P. The first landing of its kind.
We have done something nobody had ever done. This is an achievement not only for ESA, but for mankind.
But the mission also made a landmark discovery: carbon molecules that are crucial for building life on Earth. The OSIRIS-REx team hopes Bennu's surface will offer new carbon clues and help solve the mystery of how Earth got its carbon. That is, if they manage to grab a piece of it.
The asteroid is an unknown. You don't know when you get there or when you're planning the mission that this is going to be a sampleable place.
Observations made by the Spitzer Space Telescope provided clues to answer this question. Spitzer's cameras see infrared, a form of light that signals heat. In space, infrared instruments can pick out objects too dim or difficult to see, like a distant galaxy or a tiny asteroid. Spitzer was able to see how Bennu warms up when bathed in sunlight, as seen here in red. It also revealed that when the asteroid's surface rotates out of the sun, it quickly cools, appearing green and blue.
If you imagine being at the beach, during the day, the sand grains, they're very, very small. They absorb heat very, very quickly. At night, those little sand grains cool off very quickly. The sand is nice and cool.
Some materials cool more slowly. Rocks that sit in the sun all day hold on to their heat for a longer time. Based on the speed of its cooling, Bennu appeared to behave more like sand.
Bennu was heating up and cooling off very quickly. We literally expected this asteroid to look like a beach.
The kind of soft, smooth surface even a toddler could scoop up with ease.
Our interpretation of the data at the time suggested that it had a fairly benign surface.
With evidence of Bennu's smooth surface, rich in carbon, along with its nearby location, it seemed like an ideal choice.
So that's why we ended up going there. It really came from 1 million to Bennu.
August 2018, 2 years after launch, and 1 million miles still to go. OSIRIS-REx takes its first onboard image.
Bennu was still just a point source. It was unresolved. It looked like a star, essentially, in our optical navigation photographs.
Even as they get closer, Bennu's true nature remains hidden.
The fact that we were going so close to Bennu and still knew so little about its properties made it really exciting and amazing.
It's a little bit tricky. Not all the information that you need is available, so you can't evaluate, in some sense, the risk.
December 3rd, 2018. OSIRIS-REx finally reaches its destination.
We have arrived.
It's a great accomplishment. And now, with the spacecraft just 12 miles from Bennu's surface, the team gets ready to gaze upon the first close-up images of the asteroid. Excited to see a smooth and sandy surface.
I told the team we should be expecting a large beach, and so it's going to be easy to find a place to collect the sample. That is not what Bennu looked like at all. It really blew our minds when the data started coming in.
It's just rocks everywhere.
Oh my gosh, those big boulders were just not what we were expecting to find.
When we got the first images of asteroid Bennu, I was a little concerned, a little worried because the surface is very rough, very rugged.
OSIRIS-REx team member Dani Della Justina knows a thing or two about rugged terrain. She spends her weekends about an hour outside of Tucson, Arizona, rock climbing. And the rest of her days, and nights, as the lead scientist on the OSIRIS-REx image processing team. Her job, to create a detailed map of Bennu's rocky surface.
I think the big part of our role on the mission is to not just be the people that are processing the images, but that also help guide their interpretation.
Bennu is remarkably deceptive. Shadows cast by the sun alter its appearance. These two images were taken of the same location on the asteroid. The only difference? The time of day they were taken. And when it comes to finding a nice flat spot to grab a sample,
the orientation of the surface is kind of all over the place. Some of it is angled this way, and then an adjacent patch of surface might be angled that way. And as you can imagine, that creates a lot of difficulty when we're trying to find a smooth patch of ground on the surface of the asteroid. Sometimes it's really easy to see something in one of the images that we've taken of the surface of the asteroid, and I might relate back to an experience I've had rock climbing. Then I have to check myself and remember that rock climbing might give me some false intuition about what I'm seeing on Bennu. We're looking at a surface of a planetary object that is completely distinct from Earth.
one of those differences, the strength of Bennu's gravity in comparison to Earth's. Earth is trillions of times more massive than Bennu. Its strong gravity creates enough pressure and heat inside the Earth to melt rock and ultimately cook up the solid stone Dani can safely scale. But Bennu lacks that gravitational power.
Bennu is such a small object that the gravity is extremely small. It's microgravity.
Which is just what it sounds like. Very, very, very small amount of gravity.
So you're not necessarily going to compact or compress these kinds of materials. The boulders that make up Bennu might be really fluffy and porous.
So porous that if Bennu was placed on Earth under the pressure of our planet's gravity, the boulders might simply fall apart.
Maybe these boulders, once we push on them, they crumble. But we don't know that, so we cannot take the risk.
There's no way for the team to know what kind of surface they are now dealing with.
We left Earth with a spacecraft that had a lot of capabilities and was designed to handle, a wide range of unknowns. And Bennu's challenged us to the extreme.
Sometimes things don't go as planned. It's not always easy or straightforward, but there's also this incredible feeling when you know that you're seeing something that nobody has ever seen before. It's really powerful, and that sense of awe, it hasn't gone away.
For most of December, OSIRIS-REx spies on the asteroid from every angle.
We began executing these series of maneuvers to fly by closely and estimate for the first time what the mass of Bennu was going to be. And that was very important because until that point, we had a really large uncertainty in what Bennu's actual mass was. And we only had a few weeks from the time that we started doing these flybys, and we determined what we were really dealing with in order for us to learn enough about Bennu to get into orbit safely.
New Year's Eve, 2018.
Someone had the idea that it would be fun to dress up like we were going to a New Year's Eve party, because we were all going to be at work on December 31st.
As the rest of the world rings in the new year, the team faces one of the biggest challenges of the mission: to guide OSIRIS-REx into orbit around Bennu. It's the first time a spacecraft will attempt to orbit an object this small.
We're used to flying spacecraft in orbit around the Earth, around Mars, around the other large planets, and you can predict with a high degree of accuracy where your spacecraft is going to be in the future because you understand the gravity field so well.
It's the strong and persistent gravity of these larger planets that helps hold a spacecraft in orbit.
But when you're in a microgravity environment, all these other forces become significant.
One dominant force acting on the spacecraft, other than gravity, is the solar radiation pressure, or the sunlight interacting with the surface of the spacecraft.
When we talk about radiation pressure from the sun, we're actually talking about the photons of energy that are coming from the sun pushing on the spacecraft. Bennu is such a small object, this caused the spacecraft operators to have to do a kind of dance between that microgravity of the asteroid itself and the pressure of the radiation coming from the sun on the spacecraft.
The navigation team has had to model all of these forces to a fidelity that's kind of unheard of for planetary exploration.
This was a culmination of years of work and analysis and planning for this moment. Bennu became the smallest object to ever be orbited by a spacecraft, and OSIRIS-REx became the record holder for the lowest orbit ever achieved around a planetary body.
The spacecraft is now less than a mile above the surface. The new year seems to be off to a great start. But just 1 week later, Bennu has another surprise in store.
So this is what I was doing on the morning of January 7th.
While browsing through images of the asteroid, team member Carl Hergenrother notices something strange.
So I'm blinking through the images, blinking through the images, blinking through the images, and all of a sudden I come up to one image in particular where I notice what looks like a star cluster right off the edge of the asteroid, where there shouldn't be this many bright stars. And these are bright. And I'm looking at it and it's like, well, that's a pretty big star cluster. It doesn't look like any of the ones I know.
Hoping to get a more detailed view of these strange stars, Carl increases the brightness and contrast of the images and spots something even more bizarre.
Wow, these extra stars start turning into streaks.
Tiny streaks. Like the streaks that appear in images taken at night on a busy highway.
I had in the back of my mind this little nagging feeling. Maybe the asteroid is doing something that we didn't quite recognize.
He decides to investigate.
I started drawing lines through these streaks back to the asteroid. It was over probably a half-hour time when I realized it didn't come immediately at once that, oh, what I'm seeing is what I'm seeing. All these streaks kind of coming from the same place, which means what you're seeing is a kind of a instantaneous event. Boom.
The glowing dots no longer look like a cluster of stars, but bits and pieces of rock and dust flying off Bennu.
I mean, it looks like the asteroid just exploded. I walked over, I grabbed Dante, and he just turns white.
I think literally my jaw hit the floor at that point. It looks like this thing has just turned into a comet and is blasting particles into outer space. So my first response was, is this okay for the spacecraft? Immediately, we got the spacecraft team in a room within minutes to start looking at this information and saying, okay, do we need to fire the engines and get away from this asteroid, or are we okay to stay in orbit?
They can't immediately tell how big the particles are and worry that one could be moving fast enough to pack a damaging punch if it hits the spacecraft.
We quickly built up tools to analyze how the particles were moving by observing what the velocities were and the sizes.
But careful analysis reveals the particles are fairly small, ranging in size from less than an inch up to 4 inches. And more importantly, they are traveling at a relatively slow speed.
The velocities were low enough of the particles that even if they would essentially bounce off the spacecraft if they even came close.
And then the whole mood of the team changed. It's like, okay, we don't have to worry. Now, this is a really exciting scientific discovery. What is going on? Bennu is an active asteroid. How could that possibly be?
This may happen on every single asteroid that's out there. And it's just, we were the first mission that had the right instrumentation, and we're at the right distance, and we're taking the right data to actually detect this. But they all might be doing this. So this may be a common phenomenon everywhere in the solar system.
What's causing this phenomenon? Carl has a theory.
It could be as simple as just meteoroids hitting the surface constantly. You know, the meteors you see when you look up in the sky.
We might think that the solar system's done. Everything is settled in place, but that's not the case. The solar system is still under construction, so to speak. There are still asteroids that collide with other objects.
It isn't just, asteroids crashing into the Earth and killing the dinosaurs. They're all crashing into each other, and they're all breaking up and throwing off pieces. So everything is really dynamic, and you're just kind of watching the solar system evolve in real time.
Bennu's been a great puzzle. There's been things we've seen that we never expected to see, such as particles being ejected off the surface, some things that we thought we would see that we haven't.
Everyone is enormously superstitious right now. We try not to say anything good about the project because it'll jinx it, right? I mean, this is a mindset that's as old as humankind, right?
The team has no reason to be overconfident. As OSIRIS-REx circles Bennu at close range, taking thousands of pictures, there's still no sign of a safe spot to approach.
We started to become a little bit worried, wondering if we would actually find a safe location to sample.
Selecting the right site is crucial because it needs to accommodate a unique device, the first of its kind, and key to the success of the mission. At Lockheed Martin, a team spent years developing the touch-and-go sample acquisition mechanism, TAG-SAM for short.
Our approach is new. The intention to collect a large amount of material is new.
TAGSAM has an 11-foot-long arm designed to reach down and touch Bennu.
This is the only part of the spacecraft that's going to make contact with the asteroid surface. So it's about 30 centimeters in diameter. It looks like a really amazing piece of technology, but quite honestly, it's an air filter. We put this TAGSAM device onto the surface of the asteroid, and then we blow down high-pressure nitrogen gas to kind of agitate the soil and then basically scoop it up in a giant air filter.
We have tested TAGSAM hundreds of times, and we found that the contact time is very dependent upon whether or not the surface is stiff, like a very strong gravel bed, in which case the contact time will be short, or if the material is a little bit softer, it allows the TAGSAM head to sink into the surface, potentially up to as long as 10 seconds. After that, the spacecraft will fire back away thrusters and will leave the surface.
Then our job is to figure out what happened. We'll actually be able to turn it around. And if everything goes exactly right, it's not guaranteed, but we may actually be able to see right inside the TAGSAM and see if there's anything inside there that we collected. But we're not relying on that imaging data to verify successful sample acquisition. We can actually extend this way out, and we can rotate it around 360 degrees.
Think of the spacecraft like a merry-go-round.
So if you have the merry-go-round that is completely empty, if you're on your own and you're just trying to push it so it can go faster, you can do that quite easily. But then just imagine that there's another kid that comes around and he wants to get on the merry-go-round. Now you try to push it again to make it a spin that is much more difficult.
The more mass on the merry-go-round, the more difficult it is to push. The same will be true on OSIRIS-REx. If there's more mass in the collector, then the spacecraft will spin slower. By measuring precisely the change in speed OSIRIS-REx spins, the team can calculate how much sample was collected.
We can know exactly how much we have. Absolutely.
If we discover we don't have enough sample, then we have 2 more attempts, as we have 2 more gas bottles on board the spacecraft. So we can go back down for a second or a third tag attempt if needed.
November 2019. Space explorers from around the world come together for an international asteroid workshop. Members of the OSIRIS-REx team are there. And so are members of Japan's second mission to an asteroid, Hayabusa 2.
Initially, there was a little bit of a rivalry between the 2 missions. It was like, well, those guys have the same idea that we have. But we very quickly realized that we're all part of one community. And I think most importantly, what we're trying to do is really hard.
After the first Hayabusa spacecraft returned with its payload, the Japanese Space Exploration Agency decided to launch another, more ambitious mission.
We were sure we could make a better spacecraft.
In 2018, Hayabusa 2 arrived at a new target, an asteroid that turned out to look a heck of a lot like Bennu.
So when we saw this shape first, we are very surprised.
The first impression was, my gosh, we arrive at Bennu. What are we gonna do?
Its name is Ryugu.
When you show these 2 bodies to a layman, he will say these are twins.
Although Ryugu is about twice the size of Bennu, they have the same shape, and they're both carbon-rich asteroids, covered in boulders. Why are these asteroids so similar? Planetary scientist Patrick Michel, who is a member of both the OSIRIS-REx and the Hayabusa 2 teams, has a bold theory.
I propose the theory that they may come from the same parent body.
The idea is that millions of years ago, that parent body was struck by another space rock. In the aftermath, the dust literally settled, as the leftovers were drawn to each other by gravity.
This is material that has sort of come together, clumped itself together, and then through its own gravity has held itself together.
Bennu and Ryugu are collections of massive boulders, rocks, and pebbles that formed at about the same time. You might even call them distant cousins. Why these cousins have the same spinning top shape is a mystery the teams hope to unravel.
So it's kind of cool that we're both going to very similar objects that might even be related.
But there's one baffling difference. OSIRIS-REx has detected minerals inside of Bennu's rocky surface that contain the remnants of water. Water, like carbon, is a key ingredient for the development of life on Earth.
We have a very strong signal that there's a lot of water on the surface of the asteroid. Maybe as much as 10% of the minerals contain water inside them.
In comparison, cousin Ryugu is parched.
We don't have that much water. It's very dry, so fundamentally different.
Also different is Hayabusa 2's strategy of finding a landing site. They deploy several robots to the surface, equipped with a suite of instruments.
So you have a camera, you have something to measure the temperature of the surface, and something to measure the composition.
Some bots traverse the surface by hopping.
The whole robot can rotate and kick the surface and then jump.
The bots collect data and images. The team picks a sample site and releases a target marker to mark the spot. In February 2019, they make their first attempt to collect a sample.
Touchdown is very risky, so we are very nervous.
Finally, the signal comes in.
The whole control room were so excited.
I remember the scream of my Japanese colleagues when we knew this was a success.
Later, they receive a series of images from the spacecraft as it touches Ryugu's surface and pulls away. What they see surprises everyone.
Even though the surface of Ryugu looks like it's covered in boulders, as soon as a force was applied to the surface of that asteroid, you saw small particles flying everywhere.
The surface is very fragile and maybe softer than expected.
That actually gives me a lot of confidence in our sample collection technique. I think even if we make contact with one of those bouldery surfaces, the material is probably very loosely bound, easily broken apart. So in the worst case scenario where we hit the top of a boulder, I still think we're going to get a lot of sample.
While this appears to be good news for the OSIRIS-REx team, there's no guarantee that Bennu's surface will be similar.
In spite of all of the information that we've collected so far, there are still some things that we just can't know about Bennu until we actually make first contact with the surface.
When we go to see an asteroid, all our assumptions are usually totally messed up. They turn our understanding on its head.
A few months later, the Hayabusa 2 team goes for a second sample. This time, they blast a copper projectile into the surface of Ryugu to form a crater, in search of the most pristine, untouched sample they can find.
The crater does excavating for us. It takes that uppermost layer of the surface that's been exposed to solar wind or micrometeorite bombardment for hundreds of thousands or even billions of years and removes it and allows us to get a little bit further into the subsurface.
They collect this buried treasure from inside the crater and stow it. Although Hayabusa 2 has made 2 attempts to grab a piece of Ryugu, the team has no way of measuring their bounty. Unlike OSIRIS-REx, that must wait until the spacecraft returns back home. December 2019. The OSIRIS-REx team has been taking thousands of pictures of every inch of Bennu. searching for the best site to sample.
Our current image count is 53,000 images.
OSIRIS-REx will use these tens of thousands of images to navigate its way to the sample site.
So after we completed our global mapping campaign of the asteroid, we identified a sample site about 55 degrees north latitude, so pretty far up.
The team christens the site Nightingale. Near the North Pole of Bennu, this crater looks ideal.
It looks great from a sampleability perspective. It's got the finest grain material over a large area. So if we could get in there and contact the surface, we're highly confident that we're going to be able to get sample from it.
But nearby is one major obstacle.
That has a giant rock just off to the southwest of the crater. I give it the nickname Mount Doom from the Lord of the Rings.
Bennu's Mount Doom is as tall as a two-story building.
And we got to fly right over that and then down into the crater in order to get the material.
The size of the crater where they will grab a sample is not what they hoped for. This circle is the area the team thought they needed in order to safely touch the asteroid, about 164 feet wide.
There is nowhere on the surface, anywhere close to that, that is free of hazards.
The size of the new safe area in Nightingale is about 26 feet.
Our landing area is much smaller than what we had anticipated. The tag site right now is about several parking spaces, so it's a lot smaller area that we need to target.
We have to eke out every bit of error that we can in order to get this bullseye tag and get in there and collect the sample.
To safely guide the spacecraft away from danger, the navigation team needs extreme close-up images of Nightingale.
We can image an object the size of a penny on the surface of the asteroid.
These two bright spots circled in green are in the center of Nightingale. Each one is slightly smaller than a penny. With this level of detail, the spacecraft should know precisely where it is as it makes its way to the surface.
It's a very intelligent spacecraft. It can make some decisions on its own, and if it sees things go awry, it goes ahead and takes care of itself.
The spacecraft autonomously will be checking its estimate of position, and if it's predicting us to come down on a hazard, we'll have to abort and try again.
When you're flying by Pluto or going into orbit around Mars or landing on the surface of a planet, it's got to happen exactly according to plan, and there is no second chance. OSIRIS-REx, we're more like a hummingbird. We can go in, we can go back, we can go in, we can go back until the spacecraft decides, yep, I'm coming in, place looks good, let's go ahead and commit to the descent to the surface and collect that sample.
April 2020. A tough job gets even tougher as the team conducts a rehearsal of tag during a pandemic.
The whole work-at-home shutdown orders that started coming in March, they really hit our team at the worst possible time because we were right in the middle of the final testing and preparations for this rehearsal for tag. There was a handful of people that had to go into Lockheed Martin, but the vast majority of the team watched from home.
We were handing the reins over to the spacecraft to autonomously navigate itself to the surface.
We brought the spacecraft to within about 60 meters of the surface of Bennu.
Seeing for the first time the TAGSAM head descending towards Nightingale, it just kind of made it all much more real.
We were right on target, and the onboard navigation system worked perfectly. Really exceeded all of our expectations. It's really a testament to the team in how they were able to pull it off. If there's one thing that was a disappointment for the team, it's just that after working so hard to get to this milestone, such a huge milestone for the mission, there was a sense of disappointment, I think, that we couldn't be together as a team to celebrate it, to celebrate the success.
October 20th, 2020. After 2 rehearsals, the team finally gathers together as OSIRIS-REx attempts to touch the asteroid and grab a piece of it.
I was sweating and just nervous, waiting for the signal to come back.
It's 0.7 meters.
The last 10 minutes as the spacecraft was descending towards the surface of Bennu was unreal.
There were so many feelings running around in my head, it's sort of hard to articulate them in a small number of words. It was this slow motion thrill ride.
OSIRIS has descended below the 5-meter mark.
At the crucial moment, OSIRIS-REx makes the decision.
The hazard map is go for tag.
And we have touchdown! We did it!
Finally, OSIRIS-REx touches the surface of Bennu, the culmination of years of work.
I'm in awe, really. Everything went phenomenally well. We came down only 2 TAGSAM heads away from our target. I mean, I couldn't have done it better if I was sitting on the spacecraft, guiding myself down.
I mean, I can't believe we actually pulled this off. It was a good day.
In a few months, the spacecraft will leave Bennu on a 2-year journey back home. In 2023, a capsule containing precious rock and dust will parachute down to the desert of Utah. And the next step of the exploration of Bennu will begin.
We need to keep exploring. It really goes a long way into understanding who we are, how we got here, and what our long-term prospects are on this planet.
Humans look for the unknown and consider it a challenge. They want to explore what's out there. Why? Maybe it's built into our DNA.